Oh boy, fusion! What a great early Christmas present this was, wasn't it? We need to talk about the latest breakthrough in fusion tech, obviously. I'm Eric Malachite, science nerd and science fiction and horror author, and I'm joined by a disembodied voice from the void, James Fitzpatrick.
Ooh, hello.
All right, James, I think we need to do a quick breakdown on what exactly fusion is, how it happens in stars, which actually, fun fact, I learned something new about that process. It's not just gravity. It actually involves a little bit of quantum tunneling as well. Yeah. So in stars, gravity is the primary reason why temperatures are able to get as hot as they do to cause that initial fusion reaction. As I explained in a recent geographics episode that I wrote, stars form from stellar nebulae. Gas contracts in on itself due to gravity. Once there's enough mass, you get a protostar, a star-like object that does not actually have any fusion going on in its core. But once there's enough mass, the gravity becomes strong enough and the fusion reaction starts, right? So how does this relate to fusion? Well, stars are a balancing act between the force of gravity and the nuclear reaction at its core, right? Obviously, we can't create artificial gravity, at least not yet. My nerdy heart is still holding out hope for that, though. There are a couple of different methods for achieving this without the ability to simulate gravity, basically, the gravitational tug of war that exists inside stars, right? We've done about 70 years of research, and most of it has been with the first type of fusion reactor design, and that is magnetic confinement fusion.
Which I know they're still working on that with that over in England. They have a facility that made a breakthrough earlier this year.
Yeah, and France is currently working on that as well. So pretty much all the time when we're talking about magnetic confinement fusion, we're talking about tokamaks. I think there are a couple other designs too, but tokamaks are the most common. They're the ones currently active in development. China's fusion reaction, which was sustained for about 17 minutes, I think, you mentioned, is a tokamak. And I think France's is a tokamak as well, isn't it?
Yeah, southern France and the one that's near Oxford in England. Those are all tokamaks.
And I think this... And I agree with Kyle Hill when he says this is not just a breakthrough, this is reaching a milestone. Anton Petrov does not agree with that, but scientists are going to disagree. Engineers are going to disagree whenever history happens, right? We know that magnetic fusion uses magnetic fields to confine fusion fuel in the form of a plasma. This is the primary research that's been done over these past 70 years. This is not the technique that was used to make this milestone breakthrough. What we're talking about today is inertial confinement fusion. So basically how this works, to catch everyone up who has basically not been paying attention to YouTube over the last 8 days, Lawrence Livermore National Laboratory, LLNL, in California, managed to get a net energy gain from a nuclear fusion reaction. There's a bunch of caveats to that, though, and we're going to go over that. So the experiment, or rather how the reaction was created. We bombarded a pencil eraser-sized pellet of fuel containing deuterium and tritium. Basically used 192 different lasers to generate 3.15 megajoules. So about enough energy to heat a kettle of water if you use a pour-over coffee maker like I do. So deuterium and tritium, they're isotopes of hydrogen. It took 2.05 megajoules to achieve this reaction, but there's a big asterisk on this, and something that, MSNBC and the major mainstream news outlets are just completely ignoring. And that's the amount of energy that was lost from the laser system itself, because this facility is absolutely massive. They put 300 megajoules into this system to get 3.15 megajoules out of it. So there are different levels to this, and the reason why this is still a net positive is because they're only counting how much energy was actually put into the reaction, which is 2.05 megajoules, I just mentioned, right? So we get a net energy gain, which is huge, absolutely huge. That's a big deal. I mean, we can't ignore the detractors to this, right? The 300 megajoules of energy put into these extremely inefficient lasers. There's a really good graphic that Kyle Hill used in his video that basically breaks down how each phase used and lost energy on the way to the end result. And actually, I want to talk about milestones for a second before we get to the science fiction part, the speculation that we're going to end up doing, right? Milestone 1 is fusion ignition, right? Check. We've done that. I think the first time the reaction produced as much energy as what was put into it, and now we have reached milestone 2. Get as much, if not more, energy than you put into the reaction. Milestone 3 is putting less energy into the entire system and getting net energy gain. Okay, so milestone 4 would be harness that power. So here's the problem. We've reached milestone 2. We know that we can create the reaction. A lot of physicists, a lot of nuclear engineers have come on and said inertial fusion is not going to be the way forward as far as producing energy goes. In fact, the nice people who created this reaction, they're actually working on more efficient ways to create nuclear bombs, or as they call them, nuclear deterrence. But there's an important point, and I want to get to this real quick. We've only done this once. The reaction lasts about as long as it takes to blink, literally the blink of an eye. Now, CNBC claimed that the reaction got 10 times hotter than the sun, but listed a temperature of 3 million degrees Celsius. And this is kind of a pet peeve of mine. Right now, you know, the core of the sun is 15 million degrees Celsius, right? Outer core is around 7 million degrees Celsius. The sun's mantle is around 2 million degrees Celsius. The sun's surface is 5,500 degrees Celsius. The photosphere ranges from 6,000 degrees Celsius to 4,000 degrees Celsius, several hundred kilometers up. And the corona is 1 to 2 million degrees Celsius. So how exactly is it 10 times?
I've seen other figures say that, like with the facility in the UK, they reach temperatures of 150 million degrees. So saying that's 10 times greater, I could see you spinning that.
Oh yeah, absolutely.
But 3 million, yeah.
Yeah, 3 million ain't.
Not in the context of what we're discussing today. No, it ain't. Right.
So, bottom line is, 2 megajoules of energy to get 3 megajoules of energy is not a high yield, exactly. To top that off, it's expensive as hell to create these fuel capsules. They cost tens of thousands of dollars, and tritium itself is super rare. So I think a gram of tritium costs about $1 million, right? So tritium is rare on Earth. There is synthetic production possibility, but this would require lithium. And lithium powers batteries for all kinds of stuff like cell phones, cars, etc. Mining can possibly damage the environment too. So there's a concern there, especially as we're dealing with all sorts of stuff that nasty effects from humans, right? Humans
up being all human-y.
So Tony Ralston, a lecturer in nuclear energy from the University of Cambridge, recently appeared on the Philip DeFranco show. And I love Philip DeFranco. My wife and I watch him all the time. So he thinks this isn't going to lead to fusion reactors in the future due to tritium's rarity on Earth. Okay. The lasers also being wildly inefficient and the cost of the fuel pellets are also points that he touches on. If we're only talking about sourcing materials from Earth, that's a good point. But you know me, you know I can't help but speculate on stuff like this. So, James, did you know that asteroids and meteorites have been observed to possess tritium, and not just possess tritium, but have it in abundance? In fact, what's really interesting about the speculative field of asteroid mining, is that it's slowly becoming more real. And we're going to get to this specifically in a little bit. What's your take on this right now?
I am on your side with this. When you say that it's rare on Earth, my first thought goes towards asteroid mining, because as of right now in 2022, it's a lot closer to science fact than science fiction than it ever was before. Like, there are multiple nations actually taking steps to being able to successfully mine an asteroid and return with the yields.
Yeah, absolutely. So I guess if we need to break it down to make inertial fusion viable for a reactor, we would wildly need to increase the efficiency of the lasers, right? These are honking massive things, too. They're massive tubes. They consume a massive amount of energy. I mean, massive probably doesn't even cover it. I mean, 300 megajoules is a lot of energy.
Yes, it is.
Especially when you consider that a lot of that energy ends up being lost. These lasers need to be way more efficient. We also need to increase the energy yield. Right now, it's not very good. We also need to bring down the cost of fusion capsules. And most importantly, find a way to harness the energy from the reaction. Right now, we don't have a way to do that. So while I agree that inertial fusion is not viable right now with the current technology, I do not think we should completely rule it out. And the reason why is because we need to take pressure off of Earth's resources. We have done a lot of damage to the planet, and mining itself is a big problem. And this is something that Kyle Hill didn't touch on, the environmental impact of lithium mining. It's bad. There's a lot of lithium in the Earth's crust, and you can get tritium from lithium, but I think ultimately asteroid mining is going to be our go-to for this. So what I want to point to is that asteroid mining is actively in development right now. There have been a couple companies that have been bought out and basically changed their goals and what have you. But here's how I think this could work.
Circling back to what you were saying about the environmental impacts of mining, I think it also has to be considered that with mining on Earth, that's one of those industries that's it's open to human rights violations. There's a lot of places around the world where you'll still find, people cutting corners. And so if we do it on asteroids, that's kind of forcing us to automate the whole process, which is another benefit.
Yeah, I agree, actually. So basically, James, how I think this is going to work is it's going to work similar to Hayabusa and probes like it that landed on asteroids and collected material for study back here on Earth, returning samples to Earth even. So Hayabusa landed on near-Earth asteroid 25143 Itakawa. Instead of samples, automated craft could land on the asteroid, collect tritium, helium-3, whatever material that we're talking about, lift off, and return to Earth. So what's fascinating about this is that companies are currently looking into the logistics of mining asteroids. Astroforge is a good example. They raised $13 million and booked their first rocket launch for a test on a SpaceX Falcon 9, right? So Astroforge is not like some of these other startups that were looking to harvest water from space for some reason. Like, water is plentiful in space, sure, but it's really not a good idea to try to harvest that in space, because Starship should be able to launch tons of it into space. We'll have more than enough, and it's just basically not going to be a viable technology going forward. Instead, what Astroforge is looking to do is harvest palladium group metals, important for tech that we use here on Earth. So we're talking about cell phones, we're talking about cars, all the stuff that we were just talking about. And tritium is one of those, right? There is a caveat here as far as like travel time. We need to have samples back before tritium reaches its half-life, but tritium's half-life is 10 years, so that's an engineering problem. So Astroforge's main goal is to end mining practices on Earth that damage the environment and deplete Earth's resources, right?
I'm on board with your theories to it. I think it's something that we do need to consider. That 5-year, what did you say, 10-year half-life for tritium? Hopefully the fact that we're mining near-Earth objects, like I know it takes 2 years to reach Mars or something like that. So that is something to consider, but I think that's a viable option for the inertial fusion because we can't keep mining Earth's resources, but we still need things like lithium. We still need, and I know that there's a helium shortage right now, so that's something that we can solve with the mining. So it's definitely something we should look into.
Yeah, the detractors for asteroid mining would most likely say, it's too expensive, right? And my answer to that would be, if infinite energy has been achieved, if we have a reactor that works, right, that has hit the 4th milestone, that's a big if, that's a hypothetical right there. Make no mistake. Infinite energy and engines capable of relativistic speeds would argue otherwise.
That's the thing. It's expensive now, but as the technology improves, that cost is going to go down.
Oh yeah, absolutely. I think one of the best jokes, and I think Philly D made this joke during his video, is it's the impossible slot machine. You put $1 in, you get $2 out every time, right? Except when you're talking about fusion is the ultimate it's the holy grail of energy, right?
I mean, look at our sun. Holy grail of energy right there.
Right, but even saying you take a gallon of seawater, which contains a lot of deuterium. That's why deuterium's such a sought after material. It's always in the conversation along with helium-3. That energy from 1 gallon of seawater equals about 300 gallons of petrol, of gas. That's an insane conversion. If you're able to do the reaction and sustain it, which we've done the reaction twice. We have not sustained it. Like we said, the lab that produced this reaction, they're not going for an inertial fusion reactor. This isn't to say that magnetic fusion won't also be viable in the future. Looking at France, of course, since the ball is in their court. But I think it's a bit too soon to say that we won't make inertial fusion viable. It may very well, as some people have suggested, the most pessimistic estimate being 100 years, because usually it takes about 20 years just to build one of these things, right? And if it uses tritium, well, its half-life is 10 years, so you can't store that material. But we do need to become less Earth-centric. Earth's had enough of already. It wants us to find other solutions. It's done. But something that's worthy to note, actually, and this is going to be the last point before I close out. Magneto-inertial fusion is a thing.
So, a hybrid system of the two?
Yes, absolutely. A hybrid system of the two. This is fusion devices that are in development that combine aspects of magnetic confinement fusion and inertial confinement fusion. The main reason for this is to lower the costs to produce these things. But since inertial fusion has successfully created a reaction, I think we're going to see a little more research poured into the hybridized approach.
I know that one of the big problems with the magnetic fusion is overheating. Like the magnets overheat, which is why the fusion that France or England did earlier this year, it only lasted about 5 seconds because the magnets couldn't handle any more than that of the 150 million degrees Celsius that was being contained within the, what's the thing called? Tokamak.
But now we want to pass it off to you. What do you guys think? Do you think inertial confinement fusion is the stuff of pipe dreams? Do you think that it's viable? Do you think that magnetic confinement fusion is the future? Do you think that's a pipe dream? We want to know. We want to know all the pithy comments. All of them. Put them down in the comments below. That's all we've got for you today, though. This is our holiday episode of Science Cat. We're going to be returning next year with more science news, amateur astronomy, and all that Wonderful stuff. So be sure to do all that algorithmic jazz, hit that like button, subscribe, and join the Discord if you love science fiction and getting into weird tangents about Elon Musk. Let's talk some hard sci-fi. See you next time, Space Cowboys.